Fed up with being interrupted when I'm on a Zoom call, I've made a device to let people know I'm busy, even if they can't see my screen or I'm not currently talking. And likewise, when I am free to chat, just listening to something on my headphones, or somewhere in between. Very much a self-taught hobbyist, I've learned loads during the project, especially about the Raspberry Pi Pico at its centre. In some other videos you can see how I gradually built up the functionality, writing my own MicroPython code to get it to do what I wanted it to. But now I want to consolidate all of that into a single how-to guide, including my new 3D printed case, without all the background development, focusing instead on the build itself, all the resources for which are available on my new website. So if you want to make your own, just keep watching. The final challenge when making my prototype was finding some way to mount it on the laptop screen. And while my Lego bracket kinda worked, I quickly realised I needed a new approach to packaging the whole thing. The electronics did exactly what I wanted them to do, all rather let down by the clunky Heath Robinson aesthetic. And to answer this, I decided it was time that I got into 3D printing, which I'd resisted so far, thinking it was too difficult or too expensive. Neither in fact proved to be the case. Yes, designing my own parts had a steep learning curve, but my budget Ender 3 Neo, bought in the Creality New Year sale for just £139, has been great value, once I got it working, but that's another story. Like the code, the files for the 3D prints are on the website, and we'll come to the individual parts a bit later. But first, let's look at the electrical components, starting with the Raspberry Pi Pico, and as I'm dispensing with a breadboard, I've got the one without the soldered headers. This time, I'll be wiring directly to the pins, and as you can see from the solder, I've already had a trial run. Next up is my text display screen, with an I2C interface. But don't worry if you don't know what that means, as I didn't when I started the project. All will become clear. Then, for 360-degree visibility of my interruptibility status, I've got a nice big RGB LED, which handily has built-in resistors. Then finally, to switch between the status colours, I've got some buttons, which like everything else, I got from the Pi Hut. Do shop around, because you can get some bargains from other suppliers, but at less than £10 for more buttons than I know what to do with, that was a deal it was hard to argue with. And of course, more convenient getting it all from one place. Components assembled, let's get back to the case design, which I've done in Tinkercad. Way back in the day, I'd done some 3D design using a thing called Bryce, and it's a tribute to Tinkercad's usability, how quickly I was able to dredge up that knowledge and make something new. But I'm not going to go through the design development here. Instead, I'll show you exactly where to find the finished STL files, which is the download section of betapracticus.com. In this instance, the files aren't actually on the website itself, but on the GitHub, to which my site links, mainly because the code was already there to support my previous video, and I wanted to keep everything in the same place. We'll be using the same MicroPython program again, so I won't go through that in any detail, just touching on installation a bit later on when we've got everything wired up. And here are the CAD files, each with a handy preview. We've got the front and the back of the case, the hollow post for the LED, and the screen brackets, which whilst they're designed for my Lenovo laptop, will be suitable for lots of others as well. Finally, we've got the wiring schematic for the breadboard version, which is essentially the same as for our directly soldered one, so we can download that as well, along with the STLs and the code. Now to get our downloaded CAD files ready for printing with some slicer software. I happen to be using Cura, but there are lots of others to choose from. It's here we can adjust some of the 3D printing parameters, in particular the infill density and whether we want to support any overhangs. Then, when we hit the button, the software will turn our solid object into a series of layers that our printer can print one at a time, including the support for the top flange, which is shown here in turquoise. Then with the sliced file, the G-code, saved to the printer's microSD card, we can start printing the first of our components, which, according to Cura, will take 37 minutes, and use 2 grams of filament. The bit you can see being printed here is the support cage, which will simply break off afterwards, so we don't need to worry that it looks a bit rough. The sides of the cylinder, that we do care about, are looking nice and smooth, not at all bad for a budget printer. Now for the screen brackets, which fit into either end of the case. A flanged boss allowing for the angle to be adjusted, and we're going to use that support again, just to keep them nice and tidy. We're actually going to need 2, one for the left and one for the right, but we've only got one STL file. Not a problem, because Cura makes it really easy to make a mirrored version, flipped on one of 3 axes, and then sliced again on that orientation. Just note that when you come to save, it will overwrite the previous one, so best to change the name of the first G-code file, then you won't end up printing 2 of the same. Once again you can see the support for the flange, which will break off afterwards, leaving a nice clear channel to fit into the recesses on the case halves, which we come to now. Unsurprisingly, the design of these was quite a bit more complicated, taking a fair few iterations before I got everything right. Along the way, I learnt how to combine simple solids and holes to make relatively complex shapes, and what would or wouldn't print successfully. One particular challenge was to find an elegant way to hold the two halves of the case together, and after a lot of experimentation, I came up with this: a captive nut inserted during a pause in the print, and then printed over to hold it in place. A bolt through the top half of the case clamping it shut. In the CAD file you can see the hexagonal hole, a little bit deeper than the height of the nut, shown by the step on either side. This is the point we need to drop it in, before subsequent layers print across the hole. This is easier to show in the slicer. Going through the layers, we've got the round hole for the end of the bolt, the hexagon for the nut, and two more layers above its thickness, which is our window of opportunity for insertion, before the print head comes over again, trapping it in place with subsequent layers. Just note these aren't printed on the nut, but over it, which is why I've gone for straight sides rather than a round hole. And here are our captive nut assemblies in the case. You can just about make out the hexagonal void, under what's evolved into more of a slot than a straightforward hole. And after grouping everything together and exporting as an STL, we're ready to slice. But before I do, there's one thing I want to do in Cura first, which is to rotate my design. This is done in a very similar way to mirroring. The reason is that sideways on I get a better access for dropping in my nuts. I may even be able to do it on the fly without pausing at all. Then once again changing my infill settings to 100%, I can hit the slice button. And when I remember to put in my SD card, save the G-code to that, which when safely ejected can be popped in the printer. This time I'm not using supports. All my slopes are 45 degrees or less, even the countersinks on my bolt holes, so I should be fine, especially with my solid infill, which as my case walls are only a few millimeters thick, doesn't use that much extra filament. What I do need to keep an eye on is the height, especially when the Z-axis approaches 6 millimeters. This is layer 30, which is when the print head has cleared the top of the hole for the nut. On my smaller experimental prints, this is where I pressed pause, fitted the nut and then resumed. But with my larger and slower print, I've got just about enough time to do this without pausing, and when the print head is busy on the other side, I can deftly, or not so deftly, prop in the nut before it comes round again. It's actually not as dramatic as it appears here, and with 2 layers leeway I've got plenty of time to line up the next one, pop it in and press it flat, so the print head doesn't hit it when it goes over. Then at layer 33 we start to cover it over. As I mentioned earlier, the filament isn't actually on the nut, it's being printed over the hole, and I've learnt that a straight bridge is very much more effective, hence the square slot rather than a circular hole. And we don't need to cover the nut entirely, just enough to give it something to push against when the bolt is tightened up, and all the layers above will give it strength. Then with all the excitement of the nut insertion over, we can leave the printer to do its thing and go and make a cup of tea. Printing the other side of the case is much more straightforward. That just has regular holes for the bolts. But when we get to it, notice that I use the straight bridges again, which for short spans can be printed without supports, saving us this job, which is removing the ones I used on the LED post and the brackets. Cura generates them automatically when slicing, and I don't really understand the settings yet, but the ones on the post seemed particularly hard to get into. But once I got through the outer shell, they peeled away easily. The ones on the mounting brackets put up less of a fight, mostly snapping away cleanly. I'll only need to do a little bit of tidying up to make them ready for the assembly, which I come to in the next bit of the film. Here are our 3D printed parts. First we've got the side of the case that the screen fits into, then the other half for all the other components. Here's where the Pico goes, the socket end slotting through the wall of the case, and the holes for the bolts for the case closure, which will screw into the captive nuts embedded into the other side of the print. Continuity pedants may notice this is different to the one we saw being printed, but you could just about see the nuts down the holes. Then we come to the post for the LED. This fits in a recess in the top of the case, flanges either side holding it in place. The laptop screen mounts work in a similar way. The fit is pretty tight, so they will rotate, but only as much as you want them to. And everything's held together by the other side of the case, which even without the bolts clips together firmly. For those, I'm using a mix of M2 and M2.5, 16mm for the case itself, and 12 for the screen. We'll need the nuts for those too. Obviously the ones for the case bolts are embedded in the print, then some smaller ones for the Pico, which when we've taken the case apart again, I'm going to fit first. I've designed this so the USB socket fits through the case wall, with a wider slot underneath for one end of the board, which it just pushes into. The micro USB easily accessible for plugging in a power cable. The other end is bolted in place, using the 8mm M2s, which push through from the back of the case, and are secured with the tiny nuts, not only holding down this end of the Pico, but keeping the other end in the slot. This halves the number of fastenings we need. Not a bad thing, given how fiddly they are. I even had to order a special super small Allen key for the job, and instead of a spanner, I just used a pair of tweezers for the final tightening. Then Pico in place, we can turn our attention to the screen, first making sure we get it the right way up. As is my habit, I've made the tolerances pretty tight, both for the board between the two captive nut assemblies and the frame around the screen itself. But with a little bit of firm pressure, it clicks into place, snug enough that it almost doesn't need the bolts, which are the 12mm M2.5s, considerably easier to handle than the M2s. Thank goodness I didn't use those for the captive nuts. And when all 4 nuts and bolts are in place, I can tighten them up with what's now my second smallest Allen key, initially held in place with a fingertip, finished off with the tweezers, and looking pretty smart with the flush hex fittings. Now we come to the LED post. The appropriately named Squid comes with colour-coded cables, each with its own resistor, and terminating with a header connector. These would make it difficult to push down my tube, but I don't need them anyway, as I'm soldering directly to the Pico, so they can be snipped off and discarded. Then the bare-ended wires feed easily into the hollow post, although the resistors need a bit of manipulating to get them in. You wouldn't know it from the outside, but the hole actually tapers in the middle, so the bottom is narrower than the top, and it's stronger where it needs to be, which is where it fits in the case, directly above the Pico, close to the pins it's going to use. Now for the buttons, which push into the square holes on the top of the case from behind. Here you can see another example of that bridging technique, like the hole for the USB socket. As with the other half of the case, this was printed without supports, proving you can span a gap, albeit a relatively narrow one, printing on thin air. As well as wasting less filament, an advantage seems to be that it generally gives a cleaner edge, but I have got a bit of burr on my last hole, which I need to remove with the tip of a needle file in order to fit my final button, which with a little extra coaxing eventually popped into place. Like with the screen, the tight fit may be enough to keep them there, but refitting with a bit of superglue on the inside of the frame will make sure they're secure. Now for the wiring, and to make sure I know what I'm doing, I've printed out the fritzing schematic you can find on the GitHub. And I'm starting with my RGB LED, just shortening the 4 wires a bit, so they'll fit neatly in the case. Then prepping them for soldering, tinning the stripped end first to make life a bit easier. Remember, the Squid has its own built-in resistors, so we don't need to worry about those, and our wires can go directly to the pins on the Pico, starting with the red going to GP9, which is the physical pin 12, and we can solder that in place, massively assisted by the bit of solder left behind from my trial run. 1 down, 3 to go, but before I get onto the black I just want to wiggle everything into place, fitting the base of the post, and pushing the red wire down into the back of the case. Then with the help of my trusty third-hand tool, I can guide the wire of my common cathode over the ground pin and hold it in place while soldering, adding a little bit more solder as required. Then exactly the same procedure for the green wire, going to GP10. And with the same for the blue one next door, that's our LED soldering complete. But before going on to our next component, let's just double check our wiring. Then it's time for the buttons, or more properly, tactile switches. And as I mentioned earlier, even though the fit is nice and snug, I just want to refit them with a bit of superglue on either side. Then knowing they're held firmly in place, I can address the connections on the back. Even though the buttons have 4 pins, these are actually 2 pairs, and we'll only need 2 wires for each. So I'm making a start by snipping off the top right and bending down the bottom left of all 4 buttons, leaving the 2 on the diagonal so I know I'm getting 1 from each pair. First I'm going to join the bottom rights. For this I'm using the leg of an old blown LED, running between the raised connectors and soldered onto each, keeping the left-hand ones well out of the way. This will be the common positive, linking to the 3.3 volt output from the Pico. We'll be wiring that up in a bit, but first, the inputs from the buttons. And for these I've raided my model railway electrics box for some decoder wire, which will be perfect for the job. I've even got all the right colours, well almost, but grey will do for my green. But we'll start with the red, stripping the insulation as normal, remembering to adjust the strivers first. Then with a little bit of solder on the top left-hand leg, we can line up our wire, and held steady in the third-hand tool, solder into place, making sure we've got a really good connection. teasing off any excess solder, so we've got a neat one too, before going on to the orange, where we can follow exactly the same procedure. A little bit of solder on the pin, a bit on the end of the wire, which lined up accurately and held steady, can be soldered into place. Then the same for my stand-in grey cable for the green button, and finally the black for the off, which turns out the LED and the test display. The other end of each of those wires is going to the Raspberry Pi Pico, where a push of the button will be detected as an input, and I just need to cut them to length to reach the appropriate pin. The actual operation of the buttons is all in the downloadable code, so I won't go into any detail here, but I do in another video if you're interested. Just check out the link above. What I will do is show you where to solder the wires. The red one going to the left-hand pin of the bottom row, general purpose input-output pin number 16. The orange wire goes to the one immediately to the right of that, and of course I got my thumb in the way when filming the soldering, but at least you can see where it goes. The grey wire for the green button goes a few pins further to the right, not the one immediately next door, the solder on that was an absent-minded mistake, but two further to the right, which is GP19. If you want more detail of the pinouts for the Pico, the Raspberry Pi website is the place to go. Finally, for the inputs, we've got the wire for the black button. This goes to GP22, which rather confusingly is physical pin number 29, but it's the 22 that matters for the code. Then with that and the other input wires neatly tucked away, we come to the last connection, at least as far as the buttons are concerned, which is the wire from the Pico's 3.3 volt output to the common positive of all four buttons. Again, it took me a couple of goes to solder the right pin, forgetting that one was half obscured by the case. But having corrected that, it didn't take me long to sort out the other end, soldering it to the rod I used to connect the 4-button terminals earlier. Then with all 5 wires tucked away as neatly as possible in the bottom of the case, I just want to make a bit more room for the screen by folding down the top connectors. And it's the wiring for the screen we come to next. As I mentioned earlier, this has an I2C interface, which uses a 4-pin connector, but to save space I'm going to dispense with the plug, and solder my wires directly to the back of the socket. We can see these on the fritzing diagram, although the image is slightly different from my screen, so we're going to have to go by the labels, and use the colours of the wires we've got, starting with grey for the serial data, soldering to SDA on the back of the connector. As far as the wiring goes, we don't need to understand I2C, we just need to get each end in the right place, and the next one of these is SCL. We don't really need to know that it stands for serial clock. Then, like just about everything, we've got a black wire for the ground, and a red one for the positive voltage, labelled VCC on the back of the socket. Now for the Pico end of things, and of course that's in the other side of the case. So I've laid each half side by side, and cut my cables so they reach when it's open, but won't be too bunched up when it's shut. The first of these is the grey wire, that's the SDA, and we need to check with our fritzing diagram to see where that goes, tracing the yellow line to GP4, the 6th pin from the right, where we can solder our wire into place. Next up is our orange SCL, which is shown as blue in the diagram. This goes to the pin immediately on the left, which just leaves the power cables. The black wire can actually go to any of the ground pins, but I'm sticking to the one I used in my prototype, just for consistency, even though it is a bit difficult to get at. Then finally the VCC, the red cable, which solders on the same power pin as for the buttons, so we need to make sure we don't disturb that connection while we're doing it. Then with the wiring complete, we can shake out all the loose ends and start the case assembly proper, inserting the 2 laptop screen mounting brackets and ensuring that all the internal wiring is clear of the edges, particularly those for the text display. Carefully close the 2 halves of the case, checking nothing's trapped between. And when we're completely happy with the fit, insert the case bolts, which push through the back and engage with the captive nuts buried in the print for the other half of the case, tightening up with the Allen key. These not only hold everything together, they also tighten up the rotation of the screen mounts, so we can adjust the angle of the display, which now we've got everything assembled, we need to get operational by installing the code. And as I've mentioned already, all of that is available via paterpracticus.com, which is also home to the resources for various other projects. In this case, everything actually lives on the GitHub, and to save you a bit of time, I've put the direct link in the description. There are actually a couple of things we need, the first being VISI.py, the MicroPython code I wrote for the prototype. Now I want you to remember that I am a self-taught amateur, and I'm certain that a proper developer would have done things very differently, but however clunky, it does actually work, and can be downloaded by hitting the button. The compressed files being found in the Downloads folder of the host computer I'm using to get the files onto the Pico. In my case a Raspberry Pi, but could equally be a PC or a Mac. A right click on that will give us some options, and I want to open it using Thonny from the programming drop-down. This is the code we want, but obviously not where we want it, which is on the Pico. I'll come to how we get it there in a second, but first we need to download one more thing, and the link to that is also on my GitHub repository, which takes us to the Waveshare wiki. Here, in Demo, are the I2C drivers we need for our screen, which we can download just by clicking on the link. The compressed files joining our Python program in the Downloads folder. Time to get them from there and onto the Pico, and for this we need to connect the two with a USB cable. From here I'm working on the basis that MicroPython has already been installed, but if you need to know how to do that, just follow the link. As usual, we don't see the Pico as a drive. We can only access it through something like Thonny, and reopening that reveals a pane on the left hand side with a space for our files. It's to here we're going to save a copy of our program, selecting Pico from the alternatives. And I'm going to name it main.py so it starts automatically when the Pico is plugged in, independent of the host computer. Next we need a bit of code from our other download, again with a right click, but an extract rather than an open, as this is a folder, not an individual file. The particular file we want is fairly easy to find, in amongst the subfolders, and this is the fella, the MicroPython driver for the Pico, RGB1602.py, and we can open that in Thonny the same way as we did our other program, and get it onto the Pico in a similar fashion, by saving a copy, although this time we must give it the same name, as it's pulled into the main program, much like a MicroPython library. And that's just about as far as my understanding of I2C goes. We've got two integrated circuits chatting to each other using a common language, in this case Python. But exactly how that works doesn't really matter. And when we run the code, we've got our text display and our LED, letting everyone know how interruptible we are, all at the touch of a button. And that's all the code we need, so we can exit Thonny and unplug the USB. And when we connect it to a suitable power source, like our laptop, our main.py program will start automatically, enabling us to tell friends, colleagues and family if we're busy on a call, or completely okay for interruptions.